Okay, in this video I'm going to keep talking about the gradient. So this is part 2 of the gradient. In part 1 I talk about how do we compute the gradient of a scalar field, as well as the basic meaning of the gradient. So gradient actually means the direction that gives the maximum increase of the scalar field if we actually move along the direction. Okay, so in other words, if I give you some kind of scalar field like f, x, y, z, if this is the scalar field I give you, so the gradient, if you don't have negative, the probability gradient actually gives us the maximum increase of the scalar field if we move along a direction that defined by the gradient. So the maximum, the negative gradient, apparently it means the maximum decrease. So if it's a negative, which means it's a decrease. So if it's positive, it means an increase. Okay, that's pretty straightforward. So negative gradient means the direction that gives us the maximum decrease of the scalar field. Okay, so apparently the negative gradient is just the negative gradient of the original one, so you put all the negative in front of the partial derivatives for this I and j and k. So that gives us the negative gradient of the scalar field. So when we talk about negative gradient of scalar field, I'll talk about this in a few minutes. Some kind of examples in application for the negative gradient. Of course, here the assumption is the partial derivative they do exist. Okay, if they do not exist, we do not have the gradient. Okay. All right. So next question: what if my gradient is 0? Like, what if my gradient of f, x, y, z is 0, 0, 0 at some point x star, y star, z star? What does that mean? Okay, that could mean either one of the three cases. Okay, first of all, this x, y, z, you achieve the maximum value at a point. So here I'm giving an example showing that if at a point, let's say this is origin, let's say this is the point, this max point here is x equals 0 and then y equals 0. So here I'm going to use the in 2D only. Okay, you can also do 3D. 2D only. So for x, y, so when x 0, y 0, you reach the maximum point over here, right? This is the maximum value you can reach. So this one, then I have f, the gradient of f x, y, then x, if x equal to x equals 0 and y equals 0, this will be equal to 0, 0. So what does this mean? This means if as the maximum, the highest point, the highest value reach, you actually don't want to move away from this point. If anyway you move away from it, you're actually going to decrease. Because I move away from here, I'm going to decrease. I go from here, I'm going to decrease. Because that's the maximum point here. So the maximum increase point is for you just stay there. You don't move. That's why you have 0, 0, 0. You don't move away from that point. Which is pretty straightforward. You don't move away from it, right? The second one is also the minimum point. So why the minimum point also has the maximum gradient of this also being 0? Because the minimum point, if I make it, you could also say, let's say another example, you have 0, 0, also fxy. You have minimum point. The reason I this minimum point is I do over here give you a little bit idea of why is this 0. If you do right over here, so what's the direction that you move that give you maximum increase? It actually doesn't matter because at this point it doesn't matter which direction you go. It's always giving you the same basically same value, right? Because it's the same. The direction is the same. It's the same as you do 0, 0, you don't move anything, it's still unchanged. Okay? Which means if you change a very small period around your point, you don't get any increase in your scalar field. Of course, the last case will be a saddle point. Saddle point is somehow like this. So this is for a 3D case, a little bit hard to see, but a saddle point is somehow like this. Let me draw it again. Somehow like this. Right? So it's kind of this point right over here, somehow right over here. So if we move a little bit across left and right, it doesn't increase the value at all. So it's the same as you now keep moving. So which means that for this point, you don't have direction that will increase your your scalar value. So it's kind of 0, 0. Okay. So there could be three cases that give you the zero gradient, which means the gradient will be 0, 0, 0 if your point is the point that it will give you the maximum value of the scalar field, or is a point that gives you the minimum value of scalar field, or is a saddle point of the scalar field. They all give you the zero gradient. Okay. You can also, if it's zero gradient, which also means it's zero negative gradient, right? Because you put a negative sign, it still be zero, right? All right. So my next question is, if a scalar field fxy, first you can also say fxyz, okay, does not have a minimum point or a saddle point. So it doesn't have a minimum point, it doesn't have a saddle point. So how can we find the maximum point at the field of the scalar field using gradient? So this is actually coming from here, right? We know the gradient, if we set a gradient to be 0, it's either a maximum point or minimum point or saddle point. But if it's not a minimum point, not a saddle point, so it must be a maximum point, right? So which means, yeah, this is when we gradient equal to 0. Because gradient 0 means either maximum or minimum point, or the saddle point. Because I know it says it's not a minimum point, it's not a saddle point, so it must be a max point. So you just have to compute the gradient set to be 0. And you're trying to, what point will give you a 0 gradient. Then you're trying to find the value associated with that point. You get the maximum value, basically. Okay. So here, example showing what this means. Okay. Assuming I have some sort of scalar field like this. Okay. So it's going up and down. Okay. Then you might have a scalar field. This is your scalar field, right? So you have basically you have a maximum point. It's kind of maximum point here, sort of it's not the global optimum point, but you have sort of a local maximum point, right? It doesn't have a minimum point, okay, because the minimum point is going all the way down, right? It doesn't include any saddle points. So when you take a gradient, you set it to be 0, right? Gradient is set to be 0. You can check a number of this x1, xy's. Okay, basically you can have, this point you have x1, y1, the gradient is 0 because that's a kind of maximum point along a local maximum point. And you could have another one, you also have local maximum point x2, y2. This x2, y2. You have x and yn, so on and so forth, right? Which means when you try to use a gradient set to be 0, and you may have multiple points, right? Okay, so what I do is just to have figure out okay, for each point I compute the scalar value. It's a scalar value associated with it. For example, I can compute what is my fx1 y1, fx2 y2, so on and so forth. So the largest value of this guy among those guys will be the maximum point of this field. Okay, so basically what you do is, if the scalar field does not have a minimum point, does not have a scalar point. So in order to find the maximum point of the field, what you do is you first compute f. Here's the step you do. First we compute a gradient x, y. You set it to 0, so you compute what is your x1. You have x1, y1, and x2, y2, and so on and so forth. Then you compute what is my fx1, y1, fx2, and y2, so on and so forth. Then you compute find maximum. Then you are done. Okay. All right. Now give an example of how we compute the maximum, give a scalar field, how to compute the maximum value of that scalar field. So here I give you a scalar field which is given by fxy is negative x squared minus 2x minus y squared plus 4y plus 1. So my question is to find the point that gives you the maximum value of the scalar field and also compute the maximum value. Okay? So according to what we said before, let's first compute the gradient. Okay? Gradient is just given by partial fxy over partial xi plus partial xy over partial y times j, and we set to be 0. Okay, so if you take a gradient of this function, I don't go to the detail but compute the partial derivative. So the partial will be negative 2x minus 2 times I plus negative 2y plus 4 times j, we set it to be 0, okay? Which means this guy has to be 0, this guy has to be 0, so which means I set it to be 0, 0, so x is negative 1 and y is 2. So that's only, since this is the only point that I have, so I don't have to go over here because I only have one point here. So I don't have to actually check the difference. So this point definitely gives me the maximum point. So I also need to compute the maximum value, which means, oh, I just replace my x, y by this value. Try to figure out what the value I get. Okay, what I do is, oh, I replace the function over here, replace x by negative 1 and y by 2. Okay, so I have this guy reply x by negative 1 and y by 2. So you compute the value. The value give us, the actual value give us 6. Okay, right? So I can compute the maximum value, which is 6, and the point is negative 1 and 2. That's the point associated with this value. Okay. So last one, talk a little bit. Why do we talk about gradient? And there are a lot of applications for gradient in different aspects. One of the very popular one is in the AI called artificial intelligence. If someone know about the AI, especially we talk about deep learning. Okay, so one of the very popular one is, if you know, if you're aware of, for deep learning is called classification. For example, you have a number of cat and dogs, the pictures, right? I want to train some kind of AI machine learning, deep learning algorithm, which typically given by neural networks. I'm trying to tell, hey, is this cat or dog? Okay. So you want to train this algorithm because the neural network is a standard structure. It has all kind of parameters in the neural network, including how many layers, how many neurons in each layer, as well as the weights you put for different neurons. So anyway, so the main idea is that, hey, I want to tune my parameters in my neural networks so that if you give me a picture somewhere over here, I'm going to tell you if it's a good cat or dog. With very high probability of successful. Okay, it's pretty successful. That's what we're trying to do. So essentially, this convert to a problem is, oh yeah, because so typically what you say is, I'm going to the algorithm works is, oh, I give you different kind of images, right? The input for the images could be pixels or different kind of things. The input is x. Assume input is x. It has been very high dimensional one, and also I have a sigma, which is a parameter of my neural network. Then my output from here is called fx sigma. So this f is what coming from the function defined by the neural network, and x is the input. Sigma is a parameter used in the neural network. So this is my predictive value from the neural network. And this y is my actual labels. For example, if my f tell me, oh, this is a 1, which means, oh, if it's a dog, for example, and this y is a cat, which is bad, you know. If it's a dog, it's the same, so it will be 0, which means you do a square, be 0. The whole goal is, hey, I'm trying to minimize the predicted value from the neural network and the actual one. The difference is squared difference. Trying to minimize that, which means I'm trying to make sure they are the same. Which is then you give us very good. If my model actually is really close, they are really the same for all different samples, for example, with all different examples, then my model is really great. Okay, so essentially you can see this, try to figure out, oh, I want to minimize some function, right? We restrict certain parameter. Remember, when we try to do the negative gradient, you try to maximum, it's a maximum decrease of the scalar field. So you sort of can consider this is a scalar field of my sigma, because for different sigma you actually have different values, right? So you're trying to figure out what is sigma. What the typical algorithm is trying to do is, hey, I'm going to update my sigma, which means, oh, if I'm giving some field like this, I just draw it in the 3D, some field like this, kind of like that. If at a certain point I'm decide direction where I should go to decrease my value, basically, right? So what I do is your sigma is equal to sigma minus gamma and a gradient of course with respect to sigma, right? Take it to all stuff with respect to sigma and that time of gamma. Gamma, this guy called learning rate. What this means is, oh, I'm deciding if let's say if this is a global minimum, this is the best model I can find out. If you're at this point, I'm going to decrease a little bit, continue, it will drive me to the lowest point, and will hopefully give me 0. If the error is 0, which means you have 100% success of predicts labels. Okay, so learning rate. Why do you have learning rate? Because you don't want one step going too far away. Let's say you draw all the learning rate too high. You draw really already past the minimum point, which isn't good. That's why you don't want this learning rate to be too big, and you don't want it to be small, because if it's too small, you move very, very tinily. Okay, but the whole point is to use the gradient to actually decrease your scalar value, which means you decrease the difference between these two. That's what the gradient can be very helpful in a lot of these even advanced machine learning algorithms.